Hi, this presentation is part of a wider user uptake strategy of the European Commission. One of the aims of the strategy is to stimulate the development and use of innovative downstream applications that incorporate Copernicus data and services. My name is Bruce McCormack. I'm here representing EUROGI, the European Umbrella Organization for Geographic Information. Our overall aim is to promote the widespread and effective use of geographic information. EUROGI was asked to identify a number of use cases of Copernicus which may be of interest to practitioners in the GI community. As part of this user uptake initiative, we provide 5 case studies relating to wildfire mapping, identifying urban housing densities, land use mapping, the identification of chlorophyll in near coast waters, and this one, which focuses on the use of Copernicus for spreading fertilizer on farmers' fields. In this module, we will show you how Copernicus Sentinel-2 data can end up directing tractors on farmers' fields as they spread fertilizer or fungicide. The case study is provided by Rita Hofvater of Surgis, the Danish-based organization which supports agriculture in Denmark. This slide shows the main basic stages: satellite providing data, which is processed to produce field maps, which are ultimately downloaded into tractors to direct the spreading of fertilizer or fungicide. First of all, I think that it is useful to identify some of the relevant features of Sentinel-2. A multispectral optical sensor measures from different parts of the electromagnetic spectrum, from the visible, near-infrared and shortwave infrared parts of the spectrum. The information is collated into 13 spectral bands. Acquiring data from across this relatively wide spectral range provides useful opportunities for analysis. Resolution is, of course, a feature of considerable importance. At 10 meters, the resolution is quite considerably less than the commercial imagery which is currently available, but, however, it is considerably better than the mostly 30-meter resolution imagery provided by the free Landsat 8. In agriculture, a 10-meter resolution is perfect. In fact, in some cases, Surgis has to make the resolution 20 meters by 10 meters because of the characteristics of the fertilizer or fungicide spreader used in the field. Another important feature is the update cycle. In the case of Sentinel-2, revisiting any point in Europe takes place at least every 5 days with the same viewing angles. At high latitudes, Sentinel-2 swathes overlap and some regions will be observed twice or more every 5 days, but with different viewing angles. One of the benefits of having such a frequent update cycle is that there is more opportunity to ensure that cloud-free imagery can be obtained. This can be a particularly important benefit in areas where cloud cover can be a serious problem for optical sensors. Although not relevant for this case study, it is relevant to note that the Copernicus Sentinel-1 satellites use radar, and as radio waves penetrate clouds, cloud cover is not an issue. The chlorophyll case study, which we will show here, however, using Sentinel-1 data could also be used. It is worth looking at if cloud cover is actually to be a significant problem in your area. Finally, it is really important to note that downloading and using Copernicus data and services is free to users. The European Union has to date invested many billions of euros on Copernicus and has made a commitment to invest many more billions to ensure sustainability and further extension of the system. The provision of free data and services represents a really significant gesture by the Union. Although Copernicus is European in origin, its coverage is global, and the same free to download and use data policy applies outside of Europe. Okay, after setting out the background information, it is time to move on more directly with the fertilizer application case study. It is appropriate to note at the outset that the case study used in the example applies in Denmark. However, there's no reason in principle why it could not be extended to other countries, both here in Europe or elsewhere. In fact, CropSat is also available in Sweden, where this year they will change from the use of data supplied by commercial satellites to data supplied by Sentinel-2. Norway also has a version of CropSat, but with only few Sentinel data being used. In fact, it is relatively easy to make CropSat functional in other countries. In a nutshell, we want to produce more agricultural products of higher quality with less inputs and with lower environmental impacts. And, very importantly, we want to do this on a sustainable basis. The case study shown in this presentation can make a contribution towards achieving these goals. As indicated in the slide, across the EU, only about a quarter of farmland is classified as arable. Making more effective use of this relatively low proportion of farmland is clearly a major challenge for us in the Union. CropSat is the tool which we will look at in more detail in this presentation. It is free to use, at present only if you are a Danish farmer, and only due to the fact that Denmark data has been processed and made available for use in the tool. But as mentioned earlier, there's no reason in principle why the tool cannot be used elsewhere, provided the necessary Sentinel-2 data is available at the back end. The text in the slide mentions a vegetation index, the index which is more formally referred to as the Normalized Distribution Vegetation Index, or NDVI for short, is a key basic input into the process. The index is what is calculated from the Sentinel data. A high NDVI value indicates a high level of biomass, and conversely, a low NDVI represents a low biomass on a field. The target audience for CropSat is quite clear. It's farmers, the people closest to their agricultural land, and the ones who make the direct inputs which impact on food production and the environment. Skills needed? Very few, and those which may be required can be easily learned. Before we get into a video presentation on CropSat, it is appropriate to look very briefly at what are some of the back-end requirements. Hardware. For the farmer, just a desktop, laptop or tablet which has internet access is required. Some farmers may be in more remote areas where internet speeds are quite low. This is not likely to be a problem as the data download and upload requirements are very modest. Software. From the farmer's perspective, no bespoke software is required. At the back end, the Swedish company DataVex has developed bespoke software with the help of GIS. The farmer user, of course, would have very little interest in the back-end wizardry. In the case of GIS professionals who may wish to find out more, the company can be contacted through their web portal, datavax.se. Data. The data, of course, is coming from Sentinel-2, but that is not the end of the story by any means. It's the processing of the data which is of vital importance, including, for example, processing which deals with clouds, atmospheric effects, which can distort images, and calculating the vegetation index. All data handling is managed by the Slovenian company, Scientist, and they can be contacted through their web portal, scientist.com. The farmer application user would, of course, not be interested in these back-end matters. Let's take a brief look at some of the technical problems which arise, which are dealt with at the back end. Cloud cover can be a significant problem in some countries and at different times of the year. However, The European Space Agency, ESA for short, has a facility which identifies clouds. If the whole or part of a farmer's field is covered by cloud, as determined using the ESA cloud mask, then obviously it's not possible to develop a useful vegetation index from the satellite data, and the field data will not be shown in CropSat. In other words, the whole field will not be available for processing. In the case of very light clouds, ESA's cloud mask cannot identify them that well. In this case, fields with such clouds will be shown in CropSat, but the NDVIs for the areas covered by such clouds will be artificially low. A solution could be to show the red, green, blue, RGB for short, map as well. On this map, the farmer would be able to see the clouds, see the picture above. In CropSat, the farmer can override the areas that have been covered with light clouds. However, it would be useful if the ESA cloud mask could be improved to be able to better identify light clouds. Another issue, pixels falling across field boundaries can result in index values which are either too high or too low relative to the farmer's particular field. Such miscalculations could end up with too much or too little fertilizer or fungicide being applied, which would not only be wasteful financially, but could have adverse environmental consequences. The solution to this problem is for the pixels which fall partly inside and partly outside a particular field of interest to be deleted, and the average values of the adjacent pixels within the field to be applied to the areas covered by the deleted pixels. A third technical issue which arises is due to the fact that there is overlap between adjacent Sentinel images. This, however, is a problem which is quite easily dealt with at the back end. Overlapping images is an issue, but as shown in the slide, this is something which can be dealt with relatively easily. Satellites generate vast amounts of data. To cover a whole country, the amount of data involved becomes huge, even in the case of relatively small countries, such as Denmark. For CropSat, at the back end, all of the country data has to be downloaded. So it is clear that some tricks are needed to manage the data in a realistic way. As indicated in the slide, an FTP server can be used and granular data structures are necessary. But still, even after applying the tricks, a lot of storage space is still needed. Finally, before we get to showing the video, I think it is appropriate to show the various steps which are required from beginning to end of the process from the farmer's perspective. I will not read out each of these steps as they are clearly set out on the slide. Now, for the video part of this presentation. Farmers must meet 3 challenges to meet future needs for food production efficiently and sustainably. They must raise crop yield per hectare, improve the quality of their crops, and increase nutrient efficiency. CropSat is a free online tool designed to help farmers achieve just this. Using satellite imagery, CropSat enables farmers to map the fertilizer and crop protection requirements of their individual fields. The map is then uploaded to tractor computers for variable application of fertilizers and fungicides, taking in-field variations into account. The data comes from a Sentinel-2 satellite, part of the European Commission's Environment Monitoring Programme. In Denmark, it has been made possible to calculate the Normalized Difference Vegetation Index, or NDVI, for each of the 600,000 fields in the country. These fields cover 2 million hectares in all. The maps are updated weekly with each satellite overpass. The CropSat website is easy to use and does not require registration. CropSat is financed by Surgis and the Danish Ministry for Agriculture and Environment and is developed in the Swedish Project for Precision Farming, POS. CropSat.dk was established in January 2016. This is the entry screen where it is possible for a farmer to identify his or her area of interest. Farmers can find one or more specific fields either by entering a farm ID, identification, or by typing in an address. If a farm ID is used, all the fields belonging to the farm will be highlighted on the map. When an address is entered, all the fields linked to the address will be highlighted. In the example we will show here, an address is selected, which means the map area is instantly uploaded. It is possible to zoom the map in or out to find a specific field. When a field is selected, a drop-down box appears on the screen. Here, users can select the desired date for the Sentinel-2 A measurement data. On clicking Next, the user goes to the next screen to create a fertilizer or crop protection map. Now the field's vegetation index appears based on calculations from Sentinel-2A data. The vegetation index is colorized using values from 0 to 1. 0 indicates a low biomass, as shown in yellow. 1 signifies high biomass and is shown in green. By switching between kilograms per hectare and liters per hectare, the farmer can choose whether to create a variable rate nitrogen application map or a variable rate crop protection map. In our example, we'll create a nitrogen map. By selecting kilograms per hectare, areas with very low or very high biomass receive a low level of nitrogen. If biomass is low, the crop is too dense or weak to take up the nitrogen. If the biomass is high, the crop has already taken up sufficient amounts. On average, we want to apply 40 kilograms of nitrogen per hectare. Once our nitrogen entries have been made, we are ready to click Next. On the screen, the farmer can validate the calculations and map and then download the calculated data. If there is a need to adjust the values displayed, the farmer can go back and change the kilograms of nitrogen per hectare. If the average for kilograms per hectare is too high or too low, then it can just be overwritten. CropSat automatically adjusts and recalculates all the values to suit the new average. We are now ready to export the calculated map data. Several formats are available, including formats which can be used directly with tractor computers. We choose to export the variable rate application map in geospatial shapefile format. But first, we must type in the field name and percentage fertilizer as the file name. Then we click the shapefile button. This downloads 5 files to the computer. As you can see, there are 3 shapefiles and 2 JPG files. The JPG files show the NDVI, or vegetation map, and the variable rate nitrogen map, including the amount of fertilizer. The shapefiles are ready to be uploaded to the farm software on the tractor terminal. The terminal then reads the data file and adjusts the distribution of fertilizer or crop protection products across the field. The shapefiles can also be loaded into a GIS program for further manipulation and analysis, which may include other relevant spatially referenced data sets. During the first 6 months of 2016, only 4 or 5 pictures were available per field. This was due to the manual effort involved in uploading satellite images to CropSat. The process has now been changed to make more new data available. This means that there will be many more pictures available for the 2017 growing season. In 2017, farmers will be able to overrule the nitrogen amount on the vegetation map. The farmer may judge that the headland or other areas in the field can only take up, say, 20 kilograms of nitrogen per hectare. If so, the farmer can make a correction simply by drawing on the map. After clicking Finish, the updated data can be downloaded as before. Finally, Urogi would like to thank Rita at Certgis for providing this, what I think is a very interesting and very practical use of Copernicus data. Thank you for watching.